guys, it's me, Colin. I'm here at the Rancho Maniscale Skate Park, and I'm here to talk to you today about the conservation of mechanical energy. Let's do this. Come on, I'll show you. If we're going to define what the conservation of mechanical energy is, we have to know what mechanical energy is itself. And it's actually the sum of two different types of energies, potential and kinetic. And the conservation of mechanical energy comes in when you consider mechanical energy of a system, which is a group of objects before and after a change. And it says that before a change and after a change, the levels of mechanical energy in a system will not move. They will stay the exact same. Now, I've been told that my entire life, but we're here at a skate park to find out if big science has the right facts or if they've been lying to us this whole time. Let's do some research. In order to define the change of a system, we have to define the start of the system and the end of the system. So let's say the start of our system is a skater at the top of a ramp. Now, in order for his potential energy to be calculated, we can use the formula mgh. Let's see what happens when he goes down the ramp. Let's try and break this problem down into a little bit of an easier thing to digest. We can see our initial position here is with the skater at the top of the ramp, and our final is with the skater at the bottom of the ramp. You can see he's picked up quite some speed. You know, he's going pretty fast. There's some blurring. He's clearly has a higher velocity than he started with. So the conservation of mechanical energy, like I said before, it says that our initial kinetic energy plus our initial potential energy equals our final kinetic energy plus our final potential energy. Let's start with what we know. We know that the height of our ramp is 0.7 meters. I was able to measure. Sadly, I was not able to get the skater's mass. I didn't ask him, hey, what's your mass? Like, you know, in kilograms preferably. He didn't tell me, so we don't know that. But we do know that gravity is 9.8 meters per second squared. That's pretty easy. So, if that's the height right here, that's the height of our ramp. And we have a couple variables here to work with. Let's see what we can do. Let's start by listing out this in its expanded form. So the formula for kinetic energy is 1/2 mv squared. And that's our initial velocity. Plus mgh initial height, which is potential energy, gh, equals, same thing, 1/2 m the final velocity squared plus m the final height. Now, at this point, you may be asking, Colin, obviously the wheels have friction, obviously it's pointing like this way, free body diagram, blah, 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 there's air resistance. Okay, let's say for the sake of our argument, he's in a vacuum. Let's say for the sake of the argument that Tony Hawk decided to make frictionless wheels, okay? So now, with that out of the way, we're going to move on and start thinking about our formula here. What is his initial velocity? 0. His initial velocity is 0, so that can be canceled out. His final height, when he hits the ground, that's 0. So boom. Really, in the end, what we're studying here is mg initial height equals 1/2 m final velocity squared. So, if I clean this up a little bit, let's try and solve this. We know that if there's something on both sides, we can cancel it out. So then our formula ends up being g multiplied by the initial height equals 1/2 of the final velocity squared. And because we want to solve for final velocity, I'm going to actually solve for final velocity on one side. So let's multiply both sides by 2 and square root. And boom, our final velocity will equal this formula here. 2 multiplied by g multiplied by the initial height square rooted. So let's plug this in and see what we get. Square root of 2 multiplied by 9.8 multiplied by our initial height of 0.7 meters is equal to 1.9246 meters per second. Now, let's go back and check with our frame-by-frame analysis of the ruler, and let's see if those speeds compare. As you can see here, our skater went a total of 1 foot, 12 inches from the 11-inch mark to the 11-inch mark in just 4 frames. And if we do a couple conversions here, we'll end up equaling a total of 2.286 meters per second. So it turns out, I guess science was right in the end. I can't believe that the velocity that we calculated was
2.2.
and the velocity that the actual velocity of the skater was
1.9.
Wow, that's crazy. They were only off by
0.3.
That proves that science is the real winner in this situation. Thanks everybody for watching. You have to press it up and down. So then, you see my speedometer?
It's manual.